Okay, question 6. A teacher is demonstrating electromagnetic induction. So this is the basic idea. Okay, the generator effect. They've got a bar magnet, a coil of wire, and a voltmeter. Draw a diagram to see what's going on. So I'll do a rough one first. Sketch myself a bar magnet, north to south. Get a coil of wire. Attach that to a voltmeter. So that'll have a dial. And imagine the dials there. And then I'm going to show that wiggling in and out. So when the north gets pushed in that way, that'll deflect it that way. Woohoo! And then when I pull it backwards with the south, that's going to deflect that needle there. So we should see the needle going up, down, up, down, up, down as I wiggle it backwards and forwards. Now, that's a dodgy diagram, but it's good enough. And here is a neat little beautiful one. There you go. So basic idea, I've got the voltmeter and that's connected to the coil, and I've got a magnet wiggling in and out of the thing. How could they use the apparatus to demonstrate the size and the direction of the induced potential difference? So the size is going to be, so if you now imagine, here's my galvanometer, let's start it at 0, okay? And we've just said, well, when I push the north in, this is going to go that side. And the size of it is how far round it goes. So if I push it in really slowly, it'll only go there. If I push it in really quickly, it'll have a bigger deflection. Oh, well, the next part is when I then move it backwards, rather than going that side, there's 0 volts. It's now going to go this side. So there's the basic idea. So going back to this, move the magnet into the coil. The meter will move in one direction. There we go. So we've now proved the direction of it. Well, the next job is now move the magnet the opposite direction. And the meter, rather than going up, should go down. We'll just move in a different direction. Next one, move the magnet out of the coil. And the meter will move in the opposite direction. So one, say, move the magnet into the coil. One, move it out of the coil. And the meter will move in opposite directions. Perfect. Next one, move the magnet in slowly. And it'll make a small voltage. Move it in quickly and it'll produce a lot of voltage. Now it won't just be that, it will actually end up making a higher frequency. So you can imagine if I wiggle my magnet in slowly, I'll get a small voltage like that. If I wiggle it quickly, not only do we make a bigger voltage, but we also get a higher frequency. So that is a bigger wiggle. It makes more volts. So as you can see, a generator, the faster I move that magnet around the coil, the more voltage I make. Handy. Next one, there is a changing magnetic field. So when I teach you this, you're going to be sick of writing that word in the core of a transformer. So we said a transformer works. It's a soft iron core. I'll just write SIC there. And we have a step up transformer or a step down transformer. So a step up will have just a couple of coils here and lots here. And this will be where we input the alternating current. Now remember, it's not a lefty-righty thing. So if this is a step-up transformer, because I've got more coils on the primary than the secondary, I can instantly turn this into a step-down by putting the alternating current in that side instead. So try to remember, it's not a lefty-righty thing. It's more coils on the primary or less coils on the primary. Okay. Describe the cause of the changing magnetic field in the core of the transformer. So we put an alternating current in. Remember, it doesn't work without an alternating current. So this is a changing direction, and this induces a changing magnetic field. So you can imagine if this is this here, as I put that little bit, I'm going to have a small magnetic field, and then I'm at the top there, I'm going to have a bigger magnetic field, and then it's going to flip directions. So this magnetic field is kind of growing and shrinking and growing and shrinking, and that then gets concentrated over to there, where the magnetic field is the same and growing and shrinking, and this is going to push electrons. So describe the cause of the changing magnetic field in the core of the transformer. An alternating current is used, and this has got a change in direction for the current in the primary coil. Next one, we've got one of these transformer calculations. So go into your equation sheet, and it's the voltage of the primary divided by the voltage in the secondary is the number of coils on the primary divided by the number of coils in the secondary. Then substitute all the bits that you're given. So you can see I'm given the voltage on the primary is 230. There we go. Write that there, VP. The potential difference on the secondary is 15. There you go. VS is 15. The primary coil's 2000. There we go. Number of coils on the primary. calculate the turns on the secondary NS. Okay, now we just got to rearrange this. So now I can go, let's take that 2000 times both sides by 2000. 2000, divide both sides by 2000 because I want to get rid of that 2000. 2000 divided by 2000 is 1, so little 1's going to sit on this side, and then I'm left with divided by 2000 on that side. Do this little maths, and I'm left with, well, 1 over the number of secondaries is 0.076. Press my inverse function on my calculator. So the NS is 1 over that number. Comes to 130 turns. I think I've made a little mistake there in that should be a 6. But it works. Try it on your calculator. And then it's the next question. You do not need that. Oh God, I'm having a nightmare. Discard all those changes.